you have the floor.
Thank you, Marcel. So let me start my clock to be sure that you don't cheat with me, Marcel.
I'm very honest.
Sure. Yeah, of course. Yes. Yes, so I'm going to talk about ultra-cold atoms, which are in a disorder which is produced by a laser speckle, and we call it a quantum simulator for Anderson localization. So we are many experimentalists, because the main goal of our group is experiment, but we are collaborating with theorists in order to make theory of what we observe. And so we collaborate with Dominique Delande, who is a world-known expert on standard theory for localization. And we collaborate with Marcel and also Svetlana and Doug sometime in order to understand how the landscape theory can help us or can give a different point of view on what we observe. So for those of you who have never seen it, or those of you who do not remember, this is a typical experiment for observing Anderson localization in 3 dimensions. We have here a cloud of ultra-cold atoms, and this cloud of ultra-cold atoms do not fall, not because it's rocket science, not because we go in a small gravity, but because we suspend the atoms with coils. The atoms are paramagnetic, and with a gradient of magnetic field, we can suspend the atoms, and believe it or not, but we can observe them as long as 6, 8, 10 seconds, as you can see here. So really they don't fall, but if you don't want that they escape, they also better be very cold, and they are very cold. Now we produce a 3-dimensional speckle by having 2 crossed laser beams passing through scattering plates. So we have what is called a speckle disorder, and the atoms are here. And typically, one of our experiments consists of starting with a Bose-Einstein condensate. A Bose-Einstein condensate means many atoms described by the same wave function. And initially, there is a small interaction energy. And when we release the Bose-Einstein condensate, this interaction energy converts into kinetic energy. And now we have many atoms in an expanding wave function. And there is basically no more any interaction because the density decreases rapidly. And then we observe what happens. And this what happens. Initially, we have this distribution. Of course, it's 3D, but I can plot it only in 2D. And then you see that first it expands, and then at one moment the expansion stops, and then this is localization. So it's a direct visualization of localization. By the way, we have done that years ago in 1D, and in 1D you directly see the exponential Anderson wave function. And so why aren't we happy with what we have done here? It's because in this experiment, due to the technique which was used for this experiment, in fact, the energy of the atoms which were in the disorder was not well defined. In other words, there was a spread in energy for the atoms, and the spread in energy was such that we always had a fraction of the atoms localized and a fraction not localized. And you easily understand that if you want to measure, let's say, the mobility edge, that is to say the energy at which you have a transition from not localized to localized, if you have a spread in energy with the atoms, you cannot make a precise measurement of the mobility edge. And knowing this mobility edge is extremely interesting. You have to know that it is extremely demanding to calculate it numerically in 3D. There is no good theory for it. And so there is a challenge to try to do that with the landscape. But for us, experimentalists, the challenge is to have a new experimental setup in order to be able to load the atom in the disorder with well-defined energy. And so what we want to do with that is look carefully with a good accuracy at the position of the mobility edge, that is to say the energy which is here. If we can, if it is precise enough, study the critical regime, and we dream sometime of measuring critical exponents. And we want to study the disorder of the various properties, the influence of the various properties of the disorder, its amplitude, correlation length, etc. Okay. So the new experiment we are working hard, which turns out to be extremely difficult, consists of starting with atoms which are all exactly the same energy and load them using the Fermi golden rule. The people who knows what it means to use that. And using the Fermi golden rule, we want to transfer the atoms on a very narrow energy band in the disorder, and then we hope to be able to load the atom with a very well-defined energy, either above or below or just around. And if we can do that, not only we will be able to measure the mobility edge, but maybe to study how, for instance, the localization length scales with the distance to the mobility edge here. And then what we want to do in parallel is to use a landscape theory to estimate, to see if the landscape theory is better to estimate the mobility edge, etc. And for that, as probably many of you know, we will need to use a landscape theory not at the bottom, but to use a landscape theory at excited levels. And this is difficult, but we know that there have been recent progress on that. And so this is what we are working at now. But maybe we would like to present what we have done already. What we have done already is addressing a problem which is, so we'll see future prospect later. And what we have done already that we called short-term program when we started this collaboration was first to make quantitative prediction of 1D localization using the landscape theory. But what I want to emphasize is what we have done on spectral functions. You all know what is a spectral function. Is it here? No, it's not here. So spectral function is basically the amplitude as a function of k vector when you have an eigenstate of energy in the disorder, okay? And this spectral function is extremely rich, give a very rich information, richer than the density of state. To make a rough statement, density of state is an integration of the details of the spectral function. So knowing the spectral function is essential to understand transport in disorder. And we have done very nice experiment where we have measured in detail the shape of the localization of the spectral function. Dominique Delande is able to do nice standard calculation to understand the kind of result that we have found experimentally. And now there is a work in collaboration with Marcel and a PhD student of Marcel and Dominique Delande in order to apply the landscape theory to recover this spectral function. This is a test bed to see how well we can do this kind of calculation about this behavior of ultra-cold atoms using the landscape theory. And so to conclude, so we are working hard at experiment. We are working, or the theorists are working hard to use a landscape theory to see how good you can use it to render an account of our experiment. And once we have done this study, measuring the mobility edge, etc., we think that the next very, very interesting thing to do will be to study localization with interaction and how does it change the localization properties and the celebrated problem of many-body localization. And here again, it's only recent developments which are very encouraging that the landscape method can be extended to the case of particles with interaction between particles. And you see that what is interesting in the kind of work that we are doing is that it is experiment and theory that work hand by hand. Questions?
Thank you, Alain. Very good timing.
Bad talk,
Okay.
but good timing. Huh?
Great talk.
Great talk.
Great
No,
talk.
but Marcel say very good timing, you know. So okay.
No, the talk are always great.
Alain, for me and some of the other experimentalists on the Zoom, can you go back to your first slide, please?
Yes.
So just
This one.
yeah. So second slide. Sorry. First.
This one or not?
Yeah, this one, please.
Good.
So on the right in the box it says 3DAL. What is the measurement? What is the experimental measurement you're making?
Okay, the measurement is we look at how the height of the peak decreases with time.
What peak what are you measuring? This is
the red peak. The red peak. Okay, we make a cut. What we measure is the density of atomic. Okay, I understand your point.
I don't
okay.
know. I don't know.
Look here. Here we have the cloud, which is here, and then right. we shine a laser beam, which is absorbed by the cloud of atoms. So we make a one-dimensional integration of the 3D. This is what we call the column density. So here we plot the column density, which is a two-dimensional thing. So this is density as a function of 2D position. And what you see is that there is a decrease. And the very clear interpretation, independent basically of any model, is that there is a fraction of the atoms which escape. And we can see that they have a diffusive evolution. That is to say, the square of the mean radius increases linearly with time, etc., etc. And there is a fraction which is localized. So it's just if you look at a fraction of the atoms are above the mobility edge, and a fraction of the atoms are below the mobility edge. And then here we have a kind of asymptote for this, and this allows us to measure the fraction of atoms which are localized here. But if you have any idea of the order of magnitude, here maybe you cannot read carefully, but it's 4 seconds, 6 seconds. This is absolutely amazing, you know, because in traditional atomic physics, atoms go at hundreds of meters per second. Here we can keep the atoms in a few micrometer or even millimeters for seconds. Okay, this is real localization. You see, suddenly boom, and then stops evolving. It's amazing.
And this is all light scattering data. So this is looking at the light. This is all light scattering. What is the actual?
Not light scattering, light absorption. It's called absorption imaging. We have a laser beam, and it's just a shadow. We look at the shadow.
Okay, so it's just absorption. Okay,
just absorption.
Okay, it's just absorption. I see. And what's the atom density in your cold atom?
Difficult question. Once it's expanded, maybe there is a few 100,000 or a few 10,000 atoms over 1 cubic millimeter, I would say. So it's peanuts. It's very small. But you know, when you that when you shine light at resonance on an atom, it's absolutely unbelievable scattering called cross-section. The cross-section of an atom at resonance is of the order of the square of the wavelengths. That is to say, 1 square micron. Okay, so it's an atom at resonance absorbs like crazy.
Okay.
Why is it that the light doesn't heat up the condensate so that it gets too
It
warm
does.
and ceases to be a...
It does. We repeat the experiment. We start the experiment, we let it expand for some time, and then we take a snapshot. And then we repeat the experiment. You are perfectly correct. The measurement destroys the sample.
I see.
Just I have a question, Alain.
If you have a question about theory, Dominique Deland is online, okay? And so if you have a question on theory, Dominique will be...
I don't know how simple is it to answer the question, but the question is the following. So you say the spectral functions are really the thing that you are interested in, and you would be very interested in seeing what the landscape can do about that, about computing them. And the question is, how precise? What's your criterion to say, okay, we have something that is useful or something that is not useful? Because we can compute things, but how close do you need to be to the actual reality to have some kind of useful information?
Well, I will say a few words, and then Dominique will probably say more subtle things. In a few words, what I like to do is to understand things qualitatively. So, for instance, there is a kind of resonance in what we have observed, and we would like to see whether the landscape method can give us a good physical feeling of how this resonance happens. But Dominique, I'm sure will have smarter things to say.
Yeah, I think that we probably need to reach something like 1 to 10% accuracy for the spectral function, because then the spectral function can be used to, let's say, compute mobility edge using some self-consistent theory, but then you need a rather good, let's say, spectral function. If more than 10%, then it's useless. But I guess we can reach accuracy of the order of %. I'm quite optimistic about that.
Okay, thanks a lot.